Alright, welcome. This is the first video on Chang 7th edition chemistry. It covers, well, what we're going to cover is to see how up here we have this PDF document. We're going to be covering all the different questions that follow at the end of this chapter. And I'll be moving around this top window so that we can see each question. We're going to go one by one, and I'm going to use this space right here to actually input the answers for us. So I'll begin with question number 1. It says to define these terms: matter, mass, weight, substance, and mixture. So the way that we are going to define these terms, let's see, I'll use a sizable font. Let's see, matter. Here we go, matter. So we can define this as matter is anything that occupies space and has mass. Mass is a measure of the quantity of matter in an object. Then we have weight. Weight can be defined as the force that gravity exerts on an object. We have D, which is substance. A substance is matter that has a definite or constant composition and distinct properties. And then the last part is mixture. Mixture is a combination of two or more substances in which the substances retain their distinct identities. Okay. So these are our various terms that we just answered from part 1. And let's see, part 2 is asking us, or question 1.2, right? Question 1.2. Which of these statements is scientifically correct? The mass of the student is 56 kilograms, or the weight of the student is 56 kilograms. Well, we would have to think the units that were given are kilograms, and these usually aren't given when we're referring to weight. They're actually the SI the SI unit. We have kilogram for mass. So I would say the scientifically correct statement is the mass of the student is 56 kilograms. Okay, so we'll select this as our answer for 1.2. The scientifically correct statement is the mass of the student is 56 kilograms. Moving on to the next question, 1.3. Give an example of a homogeneous mixture and an example of a heterogeneous mixture. Okay. Well, for the homogeneous mixture, we can give, let's see, homogeneous mixture. We can do table salt dissolved in water. That's an example of a homogeneous mixture, because the salt, when it's dissolved in water, it completely dissolves. There's no more salt that's left over, right? So it would just be straight up salt and water. So table salt plus water. Okay. Now for the heterogeneous mixture. This is a bit different than a homogeneous mixture. We could give oil mixed with water, and that's an example, because when the oil mixes with water, what happens? There's separation. You would shake it up, and if you have a salad dressing, for example, you shake it up and then you set it down on the table for a moment, or over time you would watch it separate. It never really fully mixes. It's always two separate entities mixed within the container, and you can always separate. You can, as long as you can separate them. But as far as like with the homogeneous mixture, table salt and water, once you dissolve the salt in the water, you can't distinguish the salt from the water because it's all combined into one. So that's how I would answer 1.3. Okay, number 1.4 is asking us, what is the difference between a physical property and a chemical property? Okay, so physical property we can think is any property of a substance that can be observed without transforming the substance into some other substance, right? Physical properties are any property of a substance that can be observed without transforming the substance into some other substance. Whereas a chemical property is any property of a substance that cannot be studied without converting the substance into some other substance. Does that make sense? We'll get into some examples very soon. 1.5. Give an example of an intensive property and an example of an extensive property. So we have to refer back to the text on page 8, where it states all measurable properties of matter fall into two categories: extensive properties and intensive properties. The measured value of an extensive property depends on how much matter is being considered. Mass, length, and volume are extensive properties, right? So that's mass, length, and volume. Okay? Whereas more matter means more mass. Values of the same extensive property can be added together. For example, 2 copper pennies have a combined mass that is the sum of the masses of each penny, and the total volume occupied by the water in 2 beakers is the sum of the volumes of the water in each of the beakers. However, the measured value of an intensive property does not depend it does not depend on the amount of matter being considered. Temperature is an intensive property. Suppose that we have 2 beakers of water at the same temperature. If we combine them to make a single quantity of water in a larger beaker, the temperature of the larger amount of water will be the same as it was in 2 separate beakers. Unlike mass and volume, temperature and other intensive properties such as melting point, boiling point, and density are not additive. So again, melting point, boiling point, density, and let's not forget temperature, right? So there's our examples. 1.6 states, define these terms, element and compound. Okay? So for element is a substance that cannot be separated into simple substances by chemical means. Right? Element is a substance that cannot be separated into simple substance by chemical means. Now compound, on the other hand, is a substance composed of atoms of 2 or more elements, chemically united in fixed proportions. For example, H2O, right? CO2, C6H12, O6. But we'll leave it at that simple. H2O, CO2. And those would look like this. Right? Okay, so we're on problem 1.7. It says, do these statements describe chemical or physical properties? So we have A, B, C, D, E. So we have 5 different choices, or 5 different parts. So it's asking us in part A. Oxygen gas supports combustion. So does this statement describe a chemical or a physical property? Oxygen gas supports combustion. It's going to be a chemical property. Why? Why? Why is it a chemical property? Oxygen gas is consumed in a combustion reaction, so its composition and identity are changed. The oxygen is being consumed, and combusted. Right? What's the product of a combustion reaction? We know that they are CO2 and water, right? A molecule of water. So, all depending on the hydrocarbon in the reactants plus the oxygen. But when the oxygen and the hydrocarbon react, what's left over is not oxygen, it's carbon dioxide and water. So therefore, it is a chemical property. Part B. Let's see. It says fertilizers help to increase agricultural production. So fertilizers help to increase agricultural production. Well, we're going from reactants to products. We're doing fertilizers plus whatever seeds that we have, and then it's being converted into a totally different product. So it would be a chemical product, a chemical property. And the more rationale behind it, I believe, would be the fertilizer is consumed by the growing plants, right? Or the seeds, or whatever it is. You can add fertilizer at whatever stage of growth, seed, sapling, and whatever it is that we're talking about. So the fertilizer is consumed. It's kind of like an enzyme would speed up a reaction. This fertilizer can be thought of in the same way. So fertilizer is consumed by the growing plants. It is turned into vegetable matter, which is a totally different composition, right? It's being used up, and it, in turn, the end product is vegetable matter, so it's a chemical property. That's a good example. Now part C. Water boils below 100 degrees Celsius on top of a mountain. This one here is going to be a physical property. Okay, thoughts behind this one? Measurement of the boiling point of water does not change its identity or its composition, right? Water boils below 100 degrees Celsius on top of a mountain. Okay, at the bottom of the mountain it still boils. Nothing's changing there except for the boiling point. It's a physical property. D. Lead is denser than aluminum. This here is a physical property. Why? The measurement of the densities of lead and aluminum does not change their composition. Their physical properties of aluminum and of lead. And part E. What do we have? Uranium is a radioactive element. Uranium is a radioactive element. So if it's radioactive, that means it's decaying, and it's we could think of it as the amount of uranium at one point in time is not the same as it is in another point in time. So if you have a certain amount of uranium now, in 150 years or whatever it is, you could think of 1,000,000 years from now, that mass of uranium is going to be less because it decays. Which that there is a chemical property. Right? Because its composition is changing. You're going from one whole amount of uranium at one point in time, and you're not doing anything to it except for having time pass by. And that's what the thought of radioactivity is and decay. When uranium undergoes nuclear decay, the products are chemically different substances. Okay, question 1.8. We're asking, does each of these describe a physical change or a chemical change? In part A, the helium gas inside a balloon tends to leak out after a few hours. The helium gas inside of a balloon tends to leak out after a few hours. Physical change or chemical change? Well, it's going to be a physical change. Rationale behind it: helium is not changed in any way by leaking out of the balloon. Helium is helium. It's just traveling from one space to another. So, that's the rationale. Part B. A flashlight beam slowly gets dimmer and finally goes out. So you have a flashlight on, and the light beam slowly gets dimmer until it finally goes out. This is going to be a chemical change. Why? Because the battery dies. Battery goes from one amount of energy to basically having none. Part C. Frozen orange juice is reconstituted by adding water to it. Physical change or chemical change? So frozen orange juice is reconstituted by adding water to it. This is going to be a physical change. Why? The orange juice concentrate can be regenerated by the evaporation of the water. You want to ask yourself, in each of these situations, from the start to finish, from the starting point to the end point, is it possible to go back? If it is possible to go back, then it's a physical change. If it's not possible to go back, it's a chemical change. And that's because the chemical change has permanent effects. Physical changes can be reversed, where in this situation here we have the frozen orange juice concentrate is reconstituted by adding water to it. So it probably would be difficult, and it wouldn't really make much sense to do it, but in the end it is a physical change, because you could evaporate the water out of it, and then you'd be left with the orange juice concentrate. Okay, so D. The growth of plants depends on the sun's energy in a process called photosynthesis. What do we know about this? We know photosynthesis is a reaction that requires sunlight, right? Light energy, that's what photosynthesis is. The synthesis of photo or light energy into usable, consumable energy products. So it would be water, light energy, and inorganic molecules reacting to form organic molecules such as glucose, right? So in this case here we would have a chemical change. Chemical change because photosynthesis changes water, carbon dioxide, and so on into complex organic matter, as I was saying. So this is chemical change. And the last part of this question. A spoonful of table salt dissolves in a bowl of soup. A spoonful of salt dissolves in a bowl of soup. Physical change or chemical change? Well, can we go back? Yeah, we can go back. Right? We could evaporate the soup. We would be left over with the salt. So this would make it a physical change. Here we have it. Physical, chemical, physical, chemical, physical. Okay, so back to question 1.9 and 1.10. We're going to do both of these together because they're both asking for, they both want the same type of answer, as we can see. So we'll start with number 9. Okay, it's asking which of these properties are intensive and which of these properties are extensive. Length, volume, and temperature, and mass. Okay, length, is that intensive or extensive? We know that it's a measurable property, and we can ask ourselves then, does it matter how much matter is being considered? Length does. Volume does. Temperature does not. Mass does. And with that being said, length would be extensive, volume would be extensive, temperature, on the other hand, doesn't matter, does not depend on the amount of matter being considered. Temperature is temperature, so it's intensive. And D, mass. Mass does depend on how much matter is being considered, so that makes it an extensive property. Okay, 1.10. And there's only 3 parts to this. A, B, and C. So, area. Is this extensive or intensive? Does area depend on how much matter is being considered? Yes, it does. So that would make it extensive. Okay. What about color? Does the color change? If you have a handful of grass and the grass is green, and then you go to the yard and you take 3 handfuls of grass, notably from the same space of where you pulled the first handful from, does the color change? No, it doesn't. It's still green, right? So that would make it what? Intensive. Because it does not depend on the amount of matter being considered. You go to the ocean, you take let's see, I'll use a beautiful ocean for an example, like Hawaii. Certain parts of Hawaii are nicer than others, but you go and you take a gallon full of seawater, and it has a color. Let's just call it sea blue or cerulean blue. Then you go and you take a 5-gallon bucket from the same ocean. Is the color different? No, it's not. It's the same. So it's intensive. And now for the last part of 1.10 is density. We stressed this on 1.5, intensive properties. We spoke about melting point, boiling point, and density. So we already know the answer to this one now. 1.10, part C, density is going to be intensive. Okay. 1.11, 1.11. Classify each of these substances as an element or a compound. We have 4 different examples here that we have to answer for. So again, either an element or a compound. Hydrogen, water, gold, or sugar. Well, starting with A, hydrogen. We know hydrogen is just the H, right? H2. So if it's H2, then it's a diatomic, right? That means that it's an element. It's not a compound, because why? What's different? How do we differ from compound to element? Compounds can be separated by chemical methods into their elements, right? So the simplest substances in chemistry are elements. Compounds are formed by the combination of atoms. So what's that mean for this? Substances have both unique and physical properties that can be observed. But we're talking about elements or compounds here. So hydrogen is an element. Water, though, on the other hand, H2O, that's not an element, that's a compound. Because it has 2 or more in a fixed ratio. How about gold? Au, right? That's an element. And how about part D? Sugar. Like glucose. That's got carbons, hydrogens, and oxygens in it. So that would make that a compound. Okay. And that's that for that one. 1.12 or 1.12 is very similar. This one here is asking us classify each of these as an element or a compound. Sodium chloride, helium, alcohol, or platinum. Alright, so let's answer this one real quick. 1.12. Classify it as an element or a compound. Sodium chloride, a table salt. Well, we know NaCl, that's definitely a compound. Okay. How about B, helium? He, we know that that's an element. C, alcohol. That's going to be a compound. And D, platinum. Platinum is an element. We find that on the periodic table. Right? Okay, 1.13. We're going to start the review questions. We have to give the SI unit. From the International System of Units, abbreviated SI, from the French System of International d'Unit, Table 1.12 1.2 from page 9 of the text. They want us to give the SI unit and become familiar with it for length, area, volume, mass, time, force, energy, and temperature. So starting with the first three. Length. What do we know about length? Well, it's going to be meter. Meter. M. Lowercase m. That is. An area. Well, if we thought of length times width, or base times height, so that would be meter times meter is equal to meter squared, right? So meter squared. Okay. Volume. Volume is like doing length times width times height. So that's three-dimensional. So that's meters times meters times meters. So that would be meters cubed, right? Sorry. Meters cubed. Then moving on. Mass. We stated earlier mass was the kilogram, which is correct. Kilogram. Time. It's not minutes, it's not hours, it's seconds. So lowercase s. Force. This one here is not in the table 1.2 on page 9. This one can be found in chapter 5 with the gases. Force is actually capital N for Newton. Okay. Now G, part G says energy. This one here is also not in table 1.2. This one's further in the text. This one here is joule, capital J. And then this last one here, part H, temperature. This one was in table 1.2. It's not Fahrenheit, it's not Celsius, but Kelvin, capital K. And as we move along in the chapters and we start doing more math problems, we'll start to see these joules and kelvins becoming some of the more common units that we use. We're usually always going to be using these meters and meters squared. Also kilograms. This is going to be very common in our work that we do. So we're back here with question 1.14, and I'm actually going to play some background music. Okay. While we're going through these questions. So as we can see, it says for 1.14, write the numbers for these prefixes: mega, kilo, deci, centi, milli, micro, nano, pico. The numbers for the prefixes. What it's asking us is basically referring to the content that can be found on page 10, and it's table 1.3, prefixes used with SI units. And right there in the table, so we'll start with A. Okay, so it starts at the top with tera. Now, then it goes giga and then mega. So for this question, since we're doing mega, the symbol is, we'll go ahead and give the symbol as well, is a capital M, right? Prefix, symbol, and then we'll give the number, the meaning, basically, from the table. Okay. So what's mega? We can think of mega as 1 million, or the answer that they want us to give is in scientific notation, which would be 1 times 10 to the 6th power. But in this case, we can forget about the 1 times 10, or we can forget about the 1. Instead of writing it like this, 1 times 10 to the 6th, even though this is correct, the answer that they want us to give is just this, 10 to the 6th, which is still the same as that. Okay? So, this was A. Alright, next B. They want us to give kilo. And the symbol for kilo was lowercase k. And kilo is like kilogram or kilometer, which would be like 1 times 10 to the 3 power meters, right? So what we would have to give is 10 to the 3. This is the answer that they're asking us for, right? The numbers for the prefixes, 10 to the 3. Now, if we wanted to convert, if we were being asked how many meters are in 1 kilometer, we would write it like this. 1 kilometer is equal to 1 times 10 to the 6th meter. I'm sorry, to the 3. Right. Because that's telling us that 1 kilometer is equal to 1 times 10 to the 3, which is 1,000 meters. So that's how we will use these prefixes from this table. But just to answer these questions, what I circled in the green, that's what it's asking us. So for C, they're asking us for deci. From the table, deci, unless you remember it, is 1 times 10 to the negative 1 of the base unit. So the answer would be, it's either, well, at first, the symbol is D, lowercase d, and the number for deci would be 1 over 10, or 10 to the minus 1. Okay. Just remember, it's 1/10 of the base unit. So if they ask us how many base units are in 10, or I'm sorry, are in 1 deci base. Okay, the base could be interchangeable for length, mass. Could be, we could apply this to grams, we could apply it to meters, we can apply it to a whole slew of things from the metric table, right? But this here, 10 to the minus 1, is the answer that it's asking us for. Let's see, E wants milli. The symbol is lowercase m, and this one here is 1/1000th of a base, or 10 to the minus 3, right? F, micro. Micro is 1/1,000,000th, and this one here has an interesting symbol. It looks sort of like a U, but this front line in front of the U is a bit long. See? So 1/1,000,000th of a base could be written as this. Or it would be 10 to the minus 6th power. Okay? We're going to see micrometers quite a bit throughout chemistry. And if you've taken any biotechnology courses, micrometers, or microliters I should say, for volume is very common. But how we would write it is like this: microliters or micrometers, just like that. Okay, so then this next part, G. G's asking us for nano. Nano symbol is lowercase n. There we go. Lowercase n. This is going to be 1/1,000,000th. So write 1 with 9 zeros. And with that said, we never really write it like this, okay? But we commonly write it like this: 10 to the minus 9. Okay? 10 to the minus 9. And then this last part, H, pico. Like picometer, picoliter, picogram. So it's pico, P-I-C-O. And it's just a lowercase p. And this is, let's see, we have 1,000, 100,000, million, billion. So this is going to be a trillion. One trillionth of a base. Yeah, this is 10 to the minus 12. Okay. So we gotta get used to using these prefixes, or associating these prefixes with each of these numbers here, because we're gonna start dealing with a lot of conversions coming up in these next couple of questions. Or actually, there's a lot of questions that are going to be conversions. There's 81 questions in this chapter, and we're on question number 14. So that's why we're going through some of these more basic questions in the beginning, just to understand these underlying fundamental concepts as we move forward. Because chemistry, a lot of chemistry is math, using algebra to rearrange set formulas. And it helps when you know what you're dealing with and how you can convert them, and we use dimensional analysis, and we have to pay close attention to significant figures, which we'll get into very shortly. So that completes question 1.14. Question 1.15, they're asking us, define density. What units do chemists normally use for density? And is density an intensive or an extensive property? Well, for me, the way I would answer this is, density is the mass of an object, right? Mass of an object divided by its volume. D equals m over v. And chemists commonly use gram over centimeter cubed, right? That's common. Or, equivalently, chemists could use grams over milliliters. Okay? So, I just want to point something out here, is milliliters is the same as centimeters cubed. And also, cubic centimeter. So, those three terms, cubic centimeter, centimeters cubed, and milliliter, are all the same unit. Okay? They can be used interchangeably, but it all depends on the situation that the question is using it. So you want to make sure that you stick with it. If it asks you to come up with the density using centimeters, and they give you measurements in centimeters, go ahead and report the density as, grams or whatever it is that they're using over the centimeters cubed. If they're giving it to you in volume wise, you can, like liquid volume, and they're stating it in liters, then go ahead and use that. CC is pretty outdated, but yeah, CC, CM cubed, and ML are the same. So let's see, this next part is asking us, is density an intensive or an extensive property? Well, from the earlier questions, we already know that density is an intensive property. The density does not matter, or does not depend on the amount of matter being measured, right? Because the density is a set known quantity that doesn't change. It only changes when you're speaking about different substances, like for example the density of gold, or the density of platinum, the density of copper, the density of iron. All those different elements really have separate densities to them. So, and it stays. Alright, before we move on to 1.16, I wanted to just point something out here about density. So density will denote the formula as lowercase d. D is equal to m over v. Right? Mass, density, mass, and volume, respectively. So since density is an intensive property, it doesn't depend on the quantity of mass present. The reason is that volume increases as mass does, so the ratio of the two quantities always remains the same for a given material. Okay? So, if we were given a problem where it asks us to calculate the mass or the volume, and the question is stating or giving the density of the substance in question, we can rearrange this formula here so that we can come up with the answer. So we could write it like this. So So if we wanted to calculate for mass and we were given the density and the volume, what we could do is we could do mass is equal to density times volume, right? And then if we wanted to solve for volume, if we wanted to solve for volume, we could look at this either equation, or we could say, okay, if we're here at this step, volume is equal to mass divided by density, right? Which is true. Or we can look at this one here and say, okay, we can interchange the density value and the volume. So, like, switch them up. So it'd be V equals M over D, which is exactly what the volume is. So that there is how we can use the density equation to solve for each of those variables. And that's just switching up using some algebra, right? Using what we know common from algebra. Okay, so this next question, 1.16, is asking us to write the equations for converting degrees Celsius to degrees Fahrenheit and degrees Fahrenheit to degrees Celsius. So this first part, I already have it pre-written here. We have, if we're given the temperature in degrees Celsius, we can convert it to Fahrenheit. So this question mark degrees Fahrenheit would mean we're using the formula where it includes the degrees Celsius that we're given. And this formula would be the degrees Celsius multiplied by 9 degrees Fahrenheit over 9 degrees Fahrenheit over 5 degrees Celsius plus 32 degrees Fahrenheit. Okay. So there's our equation for that. We can go using this equation here, or formula, we can convert from degrees Celsius to degrees Fahrenheit. And then if we wanted to convert from degrees Fahrenheit to degrees Celsius, we can switch up this formula a bit, and it would look like this. We would have degrees Fahrenheit minus 32 degrees Fahrenheit times 5 degrees Celsius over 9 degrees Fahrenheit. Right? Right. Okay. So again, a little recap. The temperature scales. The 3 temperature scales that are currently in use are, the units are degrees Fahrenheit, degrees Celsius, and Kelvin. Kelvin is denoted as capital K, as we mentioned in the SI unit table. The Fahrenheit scale, which is the most commonly used scale in the US outside of the laboratory, it defines the normal freezing and boiling points of water to be exactly 32 degrees Fahrenheit and 212 degrees Fahrenheit, respectively. The Celsius scale divides the range between the freezing point, 0 degrees Celsius, and the boiling point, 100 degrees Celsius, of water into 100 degrees. want to include here the formula for Kelvin. Okay. If we had Celsius, if we were going from degrees Celsius to Kelvin, how we would do that is so if we wanted to know Kelvin, degrees Kelvin, or it's not even degrees Kelvin, it's just stated as Kelvin, is equal to degrees Celsius plus 273.15 degrees Celsius times 1 Kelvin over 1 degree Celsius. And that essentially will cancel out the units Celsius there. So, excuse me, we'll be using each of these formulas here right in these next coming questions. And a good figure to look at, it compares Kelvin, Celsius, and Fahrenheit, is figure 1.8 in the text on page 12. And it shows it shows 3 thermometers. Each one measures in a different unit, one in Kelvin, one in Celsius, one in Fahrenheit. And it has the same temperature, but it shows the different values of those temperatures in each unit. Okay. Alright, so we're going to start on 1.17. So this is going to deal with some math. Okay, it's stating a lead sphere has a mass of 1.20 times 10 to the 4 grams, and its volume is 1.05 times 10 to the 3rd power centimeters cubed. Calculate the density of lead. Okay, so it wants us to solve for density, and we know that density is D equals M over V. Okay, so it's density equals mass over volume, and they're giving us the mass of the sphere, which is 1.20 times 10 to the 4 grams. That may look a little misleading there. Okay, that's our mass. Alright, what's our volume? Is 1.05 times 10 to the 3 centimeters cubed. So what we can do here is just divide these, and we're going to get D, which is, we can punch it into the calculator. I use a little scientific. 1.20 times 10 to the 4 divided by 1.05 times 10 to the 3 comes out to 11.42857. So what we want to do is we're going to write this down here. 11.4285. I'm writing, see, 1, 2, 3, 4 after the decimal. What we need to do is, since we have to remember significant figures here, so we're only going to keep 2 spaces after the decimal point. So we're going to keep this at the 2. However, we see that we have an 8, so we need to round this up. So the density becomes 11.43. And we will call this, the units are grams per centimeters cubed, right? So we can write it like that, or we can write it as this: 11.43 G/cm3. Okay, it's a little misleading there again. There we go. This is our answer. And looking on the solution, that's right. So that's as easy as it gets, pretty much. It's straightforward. Alright, 1.18. Mercury, which goes by the symbol Hg. Mercury is the only metal that is liquid at room temperature. Its density is 13.6 grams per ml. So we're going to write this down. .6 grams per ml. I'm setting it up like this. Easier for dimensional analysis sake. How many grams of mercury will occupy a volume of 95.8 ml? So another way of thinking about this is, what's it? Well, you first look at it. You look at what they give you to work with, and then you look at what they're asking for. They're asking for how many grams, and we know that grams applies to mass. So we're going to be solving for the m for mass in the density formula. So similar to how we rearranged it up here, 1.15, we're going to use this formula to solve for mass. Okay, so m equals d times v. Mass is equal to density times the volume. So then we just bring this down. We're going to fill in the answers, or the data. So it's asking for how many grams of mercury will occupy a volume of 95.8 ml. So we just do 95.8 ml times 13.6 grams, and that's going to give us our mass. So on the calculator you can punch that in: 13.6 times 95.8. Okay, and that gives us an answer of mass is equal to 1,302.88 grams. So one thing that we have to note is most likely the answer that they're going to want us to report is going to be in scientific notation. So we look at each of these numbers. For density is 1, 2, 3 sig figs. And then for volume is 1, 2, 3 sig figs. And since we did multiplication, we're going to stay at 3. Okay? So here's our third sig fig because we have 1, 2, 3. Right? So we're essentially going to report an answer of 1,300 grams. But we're going to do this in such a way that it's in scientific notation. So to convert 1,300 grams into scientific notation, we have to make the number n a number between 0 and 9. It can't exceed 9.99999. It's got to be less than 10. So in this case, we're going to use the number 1.3, but we're going to now multiply it by 10, and we could do yeah, 1.3 times 10 to the 3 to the third power, right? This will be our answer. And we can't forget the units. Alright, so that's in scientific notation. So our mass is 1.3 times 10 to the, I'm sorry, it should be 1.30. Okay. Why? Because of the 3 sig figs. Just as I was trying to state the importance of sig figs, I forgot it myself when I was saying that the answer was 1.3. One could argue, oh, well, there's no difference between 1.3 times 10 to the third power and 1.30 times 10 to the third power. Well, in this case, with the scientific notation, we have to remember both significant figures and scientific notation. So there is an importance behind it. Alright, for 1.19, it states, normally the human body can endure a temperature of 105 degrees Fahrenheit for only short periods of time without permanent damage to the brain and other vital organs. And it's asking, what is this temperature in degrees Celsius? So there's a couple different parts to this question. This is just part A. There's a part B, C, and D, as we can see. So it's going to be some temperature conversions. So we look at what they're giving us. They're giving us a temperature that's in Fahrenheit, degrees Fahrenheit, which is 105 degrees Fahrenheit. And what they want us to do is convert it to degrees Celsius. So we're going from degrees Fahrenheit to degrees Celsius. And earlier we mentioned a couple different formulas here. We have this one here on the right. Right? Degrees Fahrenheit to degrees Celsius. We're going to use that one. So how are we going to set that up? You can get out your calculator, but what we want to do is start setting this up as degrees Celsius, that's what we're solving for, is equal to, we'll use a bracket. Okay, I have the bracket 105, since that's what they're giving us, right? They're giving us. And then part of the formula was minus 32, and those were our degrees Fahrenheit. And then we're going to multiply by 5 degrees Celsius over 9 degrees Fahrenheit. Okay? And we'll find out what that's equal to. So we need to note that because we have a difference with the 105 and the 32, that becomes 73, right? And then these units of degrees Fahrenheit cancel because we have this multiplication here, right? So what we're left with is this degrees Celsius, which is exactly what we're trying to find. So this becomes 73 times 5/9. So if you do that on a calculator, you multiply 73 times the fraction of 5/9, you get the answer of 40.55 repeat, right? And that would be degrees Celsius. So we're going to look at what we're dealing with here. We have 3 sig figs, right? 1, 2, 3. That's what these. I'm gonna start making these hash marks above the numbers so we can keep track. And I might try and write a little bit larger here. But we have 1, 2, 3 sig figs minus 2 sig figs. And if we recall the rules of sig figs and subtraction, which is similar to addition. Addition and subtraction have the same laws or rules for sig figs versus the different rules for division and multiplication. So because we have 2 sig figs, we're gonna keep 2 sig figs. And the 5/9 are arbitrary. So we're not gonna say 1 sig fig for these, okay? So what we're gonna do is we're gonna take our answer of 40.55 repeat, and we're gonna convert this, we're gonna round it to 41 degrees Celsius, okay? So that's what our answer is, 41 degrees Celsius. And some calculators actually have built into it a conversion, and the Casio that I'm using actually does. So I'm gonna just type this in and convert it myself. So we're going from Fahrenheit to Celsius. So that means, let's see, shift 8, conversion 37. So we're going from Fahrenheit, we're doing 105 degrees Fahrenheit. Yeah, so it gives us the 40.55 repeat. So it all depends on what we want to report it as, but we're going to report it as 41 degrees Celsius. Okay? So we can move on to part B. Part B states ethylene glycol is a liquid organic compound that is used as antifreeze in car radiators. It freezes at negative 11.5 degrees Celsius. Calculate its freezing temperature in degrees Fahrenheit. Alright, so simply we're going from degrees Celsius to degrees Fahrenheit. So we need to use one of those earlier conversion formulas. So they're giving us the temperature of negative 11.5 degrees Celsius. And we need to go to degrees Fahrenheit. So how we set this up, we have degrees Fahrenheit, that's what we want to solve for. We can fill in what they're giving us, negative 11.5 degrees Celsius times 9 degrees Fahrenheit over 5 degrees Celsius. And then we're going to add 32 degrees Fahrenheit. Okay? So we remember that the degrees Celsius cancels out, so what we're left with is Fahrenheit, and that's what our answer is going to be in Fahrenheit. Okay. So if we want to plug that into the calculator, negative 11.5 times the fraction of 9 over 5, that should give you an answer of negative 20.7, but then we have to remember that we're going to add it to 32, right? So that's going to give us a temperature of 11.3 degrees Fahrenheit. And simply put, this is our answer here to this part. So negative 11.5 degrees Celsius translates to 11.3 degrees Fahrenheit. And we can move on to part C, where it's asking us again to convert temperatures. This one here, it states the temperature on the surface of the sun is about 6,300 degrees Celsius. What is this temperature in degrees Fahrenheit? Okay, so it's giving us 6,300 degrees Celsius, and they want us to convert to degrees Fahrenheit. Okay, how we set this up: a degrees Fahrenheit is equal to, we plug it in, we'll use scientific notation to keep it simple, 6.3 times 10 to the third power. We'll try and write more legibly. There we go. And that's degrees Celsius. And we're going to multiply that by 9 degrees Fahrenheit over 5 degrees Celsius. And then we're going to add 32 degrees Fahrenheit. Okay. And that's going to give us our degrees Fahrenheit. So we remember that the Celsius cancels out, we're left with Fahrenheit, and we can start plugging this in on the calculator. We can do 6.3 times 10 to the third power multiplied by the fraction of 9 over 5 will give you the total 11,340, and we have to remember that we're going to add 32 to it. So that's going to give you 11,372 degrees Fahrenheit. And we need to state the importance of this here. We always got to make sure that we're reporting our answer to the appropriate number of sig figs. This answer right here, 11,372, is 5 sig figs. That's more sig figs than we started with, because we look at this starting number that we're given, 6,300. There's only 2 sig figs here. One may think, oh well, there's 4. That's not true. By the rules of sig figs, any number that just has trailing zeros, that means that the numbers before the zeros begin are the ones that are significant. So that makes this 2 sig figs on this number. So because we have 2 sig figs, we're going to make sure that we keep 1.1. And are we going to round this 1 right here? Well, we look to its neighbor 3, which means it's less than 5, so we're not going to round. Okay? So we're going to report our answer as 1.1 times 10. And what would be the power of this? Well, because we're essentially reporting a number of that's equivalent to 11,000 degrees Fahrenheit, that means that we're going to do 1.1 times 10 to the 4 power degrees Fahrenheit. And this is our answer. Okay, 1.1 times 10 to the 4 degrees Fahrenheit. And we can't forget the units of temperature. And then we can move on to the next part. Alright, the ignition temperature of paper is 451 degrees Celsius. 451 degrees, Fahrenheit. What is the temperature in Celsius? Okay, so they want us to go to degrees Celsius. Let's make it happen. we're going to do our degrees Celsius is equal to 451 minus 32, and these here are both degrees Fahrenheit, and this is multiplied by the fraction of 5 degrees Celsius over 9 degrees Fahrenheit, and that's equal to our degrees Celsius. So we can punch this into the calculator. 451 minus 32, that's going to give us our 419 times 5 over 9. Gives us what temperature? 232.77 repeat degrees Celsius. So we look at what we had in the beginning. We had 451 degrees Celsius, that's 1, 2, 3 sig figs. My guess is we have 1, 2, 3. Right, we're going to stop here. We look at the neighbor at the 7. That means that we need to round up. 233 degrees Celsius. Okay, and that's our answer. I'll write this a little bit more legibly. There we go. 233 degrees Celsius. That's what it converts to. 451 degrees Fahrenheit equals 233 degrees Celsius. And that wraps it up for question 1.19. We had 4 parts, so 4 different conversions. As we can see, A, B, and C, and D. And now we'll start on 1.20. Alright, so here we have question 1.20. It's got two separate parts, A and B, but each part has actually 3 subparts to it, denoted as 1, 2, and 3. So we're going to look at 120A1. It's saying convert the following temperatures to Kelvin. And the strategy behind this is we have to find the appropriate equations for converting between Fahrenheit and Celsius and between Celsius and Fahrenheit, given in section 1.5. And we have to substitute the temperature values given in the problem into the appropriate equation. So the important formula or equation that we're going to use, we're going to convert the following temperatures to Kelvin. So we're given 113 degrees Celsius, which is a melting point of sulfur. So 37 degrees Celsius, and then 357 degrees Celsius. So really we're just going from Celsius to Kelvin. So we're not going to have to, like, for example, if we were given Fahrenheit, we would have to go from Fahrenheit to Celsius, and then from Celsius to Kelvin. Unless we wanted to make up a formula to go directly from Fahrenheit to Kelvin, which can be done. But we would have to, we'd have to some way fit the Celsius in there. So we're just going to go from Celsius to Kelvin. So on page 12, they gave us the equation to convert Celsius to Kelvin, which was this. We have Kelvin is equal to the degrees Celsius plus 273.15 degrees Celsius. So we have that in brackets, and we're going to do that basically, and it's given us times 1 Kelvin over 1 degree Celsius, so that we can use that to cancel out the units. So we're going to use this. So for I, or 1, we're going to convert 113 degrees Celsius to Kelvin. So we can just simply plug in the numbers here. 113 degrees C plus 273.15 degrees C times 1 Kelvin over 1 degree Celsius. What we're left with is the Kelvin. So on the calculator you can just punch it in. I'm going to punch it in. 113 plus 273.15 gives us 386.15, and then we're going to multiply it by 1 over 1, which we didn't really have to do. So it's going to give us the total of 386.15 Kelvin. Okay. And we have to note that we're actually only dealing with 3 sig figs here because of the 113. So we're gonna keep 386. So that's our answer. 386 Kelvin. Sorry for the horrible penmanship. Okay. Part 2. We're given 37 degrees Celsius, 2 Kelvin. So we're going to do 37 degrees Celsius plus 273.15. It's that easy. We're just adding. So it comes out to 310.15, and we have, let's see, looks like for some reason they're sticking. Oh, okay, I understand. So in the textbook, not every problem, it looks like they're just doing 37 plus 273. They're not even considering this 0.15. Okay, so that's just coming out to 310. So how they want us to report that answer would be .10 times 10 to the 2 Kelvin, right? So in scientific notation, we keep our 3 sig figs. Right, because even though this is 2 and this is 3, when we add them, we still haven't, the sum is equal to 3 sig figs. And this is all before the decimal point, right? So these 3 are significant, and that's why we're keeping 3 here. Okay, understood. And it's not being reported into 2. Okay, so it needs to be addressed, the importance behind the sig fig rules for addition and subtraction versus the multiplication and division. Can't get that mixed up because they're totally different. Okay, so this is our answer there. Next, part 3, they want us to convert 357 degrees Celsius to Kelvin. we're gonna do that. Just doing 357 plus 273 is equal to 630 Kelvin. We have to convert this to scientific notation. So that's going to be 6.30 times 10 to the 2 Kelvin. Okay? And that's our answer. So we look at the next part. B. Convert the following temperatures to degrees Celsius. So now we're just going to be doing reverse. Alright. So these problems are just getting us used to using these conversion formulas. Oops. Alright, so part B. 1.20 B. And this is going to be I. Okay. So since before, or since in these previous problems we were doing Celsius plus Celsius is equal to Kelvin. Now we're going to switch this up a bit. They're giving us Kelvin. And what we're going to do, so we're starting with this. Okay? We're starting with Kelvin, and we're going to be given, we're not going to be given any Celsius. The only Celsius that we're given is from the formula, which was the 273, right? If you guys are tracking. So it's going to be our given Kelvin minus 273 equals the new value of Celsius that we want. This is what we're going to do, or use, rather. Okay, so let's go ahead and do it. So for 1, we're given 77 Kelvin, 2 degrees Celsius is something like this. 77 minus 273 is equal, and this again is Kelvin. So we can do 77 minus 273 is equal to negative 196. Okay? And that's correct. This is our answer. Okay? So the next part. Next part is asking us to convert 4.2 Kelvin to degrees Celsius. So we do that by taking our Kelvin, 4.2 Kelvin minus 273 degrees Celsius is equal to our degrees Celsius. 42 minus 273 is equal to negative 231. Whoops, I just made a mistake. If you caught it, I did 42 minus 273. It's actually just 4.2 minus 273. Okay? I have to make sure I'm addressing those decimal points. So our real answer here is negative 268.8 degrees Celsius. And since, we're dealing with rounding this number here. So that's going to make it negative 269 degrees Celsius. And that's exactly right from the text. Okay, the third part. They want us to convert 601 Kelvin to degrees Celsius. So we do that. 601 minus 273, simply 328 degrees Celsius. And that's it. That's what the textbook wants. Alright, so this next one, 21, it's asking us to express these numbers in scientific notation. A, B, and C. I got these numbers right here already written out. I'm going to try and get the rest of these problems done a little bit faster by stopping and writing them down before I continue on the recording process, because it's taken a bit longer than expected. So with these next couple problems that are dealing with scientific notation, within the textbook on page 13, let's see, yeah, page 13 is section 1.6, handling numbers. It deals with scientific notation and sig figs. So it gives us this formula, or the form, regardless of their magnitude, all numbers can be expressed in the form n, capital N, times 10 to the n power. So that's what I have here, n times 10 to the n power. Any number that is given can be expressed in what's called scientific notation. This is our standard form, right? So we're going to convert these numbers here. N, there's certain rules to this. N can't be higher than 10. It actually can't be 10. It needs to be less than 10. Yeah, capital N, this here, is a number between 1 and 10, and n, the exponent, is a positive or negative integer, whole number. Any number expressed in this way is said to be written in scientific notation. So we look at this number here, 0 point, these are 7 zeros, 1, 2, 3, 4, 5, 6, 7 zeros, followed by 2, 7. It's a really small number. So how we write this is we need to come up with our n. So the number that is between 1 and 10 would be 2.7. Okay? So we take this and we're going to make it into 2.7. And since we're going to stay with this standard form and we have our n, now we're going to do multiplied by 10, but we have to figure out now, what should our exponent be? Well, when you look at it real quick, it all depends on how you're looking at it, but just to explain it, we have 2.7 and we want to make this 2.7 times 10 to an exponent that will resemble this. So we have to remember, when we're going to the left, it's going to be negative. If we were going to the right, it would be, if we were going to move the 2.7, this decimal, to the right, it would be a positive exponent. But since we're going to start from 2.7 and we need to end up at this number here, we're going to go to the left. We're going to bring that decimal to the left, meaning that the exponent's going to be negative however many spaces that we go. So when we start with this here, we have since we're placing our decimal point here in this space, right between the 2 and the 7, we're going to move it 1, 2, 3, 4, 5, 6, 7, 8. And we're stopping here at 8. So since we moved it 8 spots, we're going to say that this is to the negative 8 power. Okay? And that's essentially the conversion. Okay? So we can say that 2.7 times 10 to the negative 8 power can also be written as a decimal form, 0.00000027. And you could plug that into the calculator, and if the scientific calculator, which it should, if it's scientific, it should have a function to easily interchange the form from decimal to scientific notation. And on those scientific calculators, you can specify how many sig figs that you want the number to be. Okay? And because it is important to note the sig figs that are here, in this number, this decimal number, how many sig figs we have? We only have 2. We have 1 and 2 with these 2 7. These leading zeros don't count as significant, and that's why our scientific notation conversion has 2 sig figs. Okay? So then this next number, 3.56. If we were going to make this a number between 1 and 10, our only option would be 3.56, right? And if we wanted, it's not if we want, we have to. We have to make 3.56 resemble 356. And how can we do that? Well, we would have to make the decimal point move to the right 1, 2 spaces. Sorry, it automatically does that. 1, 2 spaces, right? And then it resembles this number here. So what that means is we're going to call this 3.56 times 10 to the positive 2. But we don't have to write the positive sign. We're just going to say 3.56 times 10 to the 2 power. Okay? And that's how we do it. Up next, 0.96. Okay, so a number between 1 and 10 our only option here is 9.6, right? Because those are our 2 sig figs, is 96. We need 0.096, so what we're going to do, we're going to move the decimal 1, 2, 1, 2. And that's going to give us that number, right? You guys can see that. So it becomes 9.6 times 10 to the minus 2. I like this green. 9.6 times 10 to the minus 2. And it's also important to note that because this problem here in 21, I'm just going to refer to them as 21, next one's 22. But in 21, there's no units. So that's why these answers don't have units. But as we move into the chemistry further along into the semester, we're going to be using scientific notation a lot. Pretty much with pretty much any math problem that we're going to do. If it's a significantly large or small number, we're going to use scientific notation. Scientific notation makes the numbers much more convenient to work with, because who wants to write out all these zeros? Like in the first part, who wants to write out all these zeros? And in some questions they can get bigger, or smaller rather. So a good way to keep track is by using scientific notation. So that's it for 21. We can move on to 22. Alright, so 22. Express these numbers in scientific notation. So the last question I gave the tip to, like, when you're moving the decimal point to the left, that means that the exponent's going to be negative, and if we're going to move it to the right, then it would be positive. So that only applies after you declare what value your n is. The textbook is giving the strategy as this: writing the scientific notation as n times 10 to the n power, we determine the exponent n by counting the number of places that the decimal point must be moved to give n, the capital, a number between 1 and 10. So this is how the textbook is stating how to determine the exponent's power. So it's when we're determining what n is. So if the decimal point is moved to the left, then lowercase n, the exponent, is a positive integer, which is reverse from what I said. But it's only reverse because I was given the tip as after we already declared what n was. So when we just look at the fresh number that we're being given, like in A, okay, we'll apply what the text is saying. We're given this number 0.749. So in order to bring 0.749 to a number between 1 and 10, we have to move this decimal over one space to the right. Right? So that would in turn make this number 7.49. And since we moved the decimal to the right, from original to the right, to get n, they're saying n is a negative integer. The number that we were working with is smaller than 1, which is absolutely correct. So they're stating right off the bat that n will be negative. Okay? So what will our exponent be? It'll be negative 1, right? Because negative 1 will take this right here, and in turn we would get 0.749, which is exactly our original 1. Okay? So that's how the textbook is given the strategy to declare your is it negative or positive exponent. You make that determination before you or not before, but in the process of determining your n, what your capital N is, in the n times 10 to the n. N equals negative n if you have to bring the decimal point from original to the right. Okay? And n is equal to positive n, which we don't denote the positive, we just write the number, if the decimal has to be brought to the left. So we'll see that demonstrated in B, right here. We're going to use it. So let's look. So we're given this original number, 802.6. We need to convert it to scientific notation. So here's our decimal, we have to move it to the left 1, 2 in order to get our n, which is equal to 8.026, right? So since our n had to go to the left, we know that our lowercase n will be positive, right? Our exponent. So what will our exponent be? Since we moved to the left 1, 2, it's going to be positive 2. But again, we don't write this positive, we just denote it like this. Right? And that's the answer in the text. They're saying the decimal point must be moved 2 places to give n a number between 1 and 10. In this case, n, which is equal to 8.026. It's a number greater than 1, so n is a positive integer. Alright, so we'll stick with that, because that makes the most sense and it's how the textbook is stating to do it. So let's apply it to this next one. We have our original number here. There's 6 zeros after the decimal point. So we have 0.00000000621. So we need to get this number here, 621, to a number between 1 and 10. So in order to do it, we have to move this decimal point over to the right. 1, 2, 3, 4, 5, 6, 7 spaces. Basically move it right there. In turn, or as a result, I should say, n is equal to 6.21, right? But let's complete it. Since we moved our n to the right, the exponent is negative n. But what's our exponent number? Well, we moved it 1, 2, 3, 4, 5, 6, 7. So it's going to be -7. Okay. So our answer, I'm just going to do it in green here, is 6.21 times 10 to the -7. And that's pretty much how we're converting. Alright, so for 23, we have to convert these numbers to non-scientific notation. We're given 2 numbers, A and B. For A, we have 1.52 times 10 to the 4th power. And then for B is 7.78 times 10 to the -8 power. So starting with A. Alright, so there's a couple different ways that you could do this to get through it really fast. You could just input this into your calculator and press enter, and then it's going to give you what the answer is. But if you wanted to do this out by hand, which is how we're going to do it, we would do it like so. We have our lowercase n, which is our exponent. We know it's equal to 4. So that means that we're going to move this decimal point from 1.52 over to the right. 4 places. Right? So here. 1, 2, 3, 4. So this becomes 15,200. Okay, and in the textbook that's correct. Why did we move it 4 places to the right? Well, lowercase n, the exponent, was positive 4. So we moved it 4 places to the right from the original number, which was given to us in scientific notation, as I just demonstrated. So let's do this next one. we have 7.78 times 10 to the minus 8. So we know n is equal to -8. Okay, so we have 7.78. We're going to be moving the decimal from n 8 spots to the left. We're going to go 1, 2, 3, 4, 5, 6, 7, 8. And we have to fill in the zeros. 1, 2, 3, 4, 5, 6, 7. We can put a 0 before the decimal point. Alright, so that makes 0 point. 1, 2, 3, 4, 5, 6, 7, 7, 7, 8. This is our number. Okay. One way that I do these really fast, like mentally, is I just look at the number that we're given as n, like for in this example 7.78, and the exponent that they're giving us is -8. So, and for me, I'm so used to doing these, I do them real quick. I can automatically look at this and say, okay, because the exponent is -8, there's going to be 7 zeros before the original number. 7 zeros before this 7.78. And that's exactly what we have in the end. So that's how we would convert numbers from scientific notation to non-scientific notation. Alright, question 24 is asking us to convert more numbers from scientific notation to non-scientific notation. So I'm going to try and just go through these quick. We're given 3.256 times 10 to the -5. What they want us to do is we need to add enough zeros to get the original non-scientific number. Since our n exponent is -5, that means that we can simply move the decimal place to the left of 3.256 by 5 spaces. In the end, we're going to be left with a number 0.4 zeros, 1, 2, 3, 4, 2, 3, 2, 5, 6. This is our number. Okay, you can check that on a calculator and do it, but we simply just moved it 1, 2, 3, 4, 5, and we had 0, 0, 0, 0. Right, and that's what we ended up with. So this is our number, and from the solutions in the book, this is correct. So our next number, part B, 6.03 times 10 to the 6. Our n exponent is +6. So we're going to move this decimal from our original 6.03, we're going to move it to the right 6 spaces. And because if we look at this n, we have a decimal point here, and then we have 2 sig figs. So with that being said, since our n exponent is 6, I'm simply going to write this number as 603, and I'm going to add 4 zeros after the 3. 1, 2, 3, 4. And our final number is 6,030,000, which is correct. How did I just know to add 4 zeros to it? Well, because I knew that we had to move the decimal 6 spaces out to the right. But we were already given these 2 digits. So these 2 count as the first 2 of these 6. And what remained were these 4. 1, 2, 3, 4. Okay, and that's how I made sense of that mentally. That's how a way that you can do these mentally quick, and it's always good to check yourself and go over these math problems at least twice. That's one thing I've definitely learned from these chemistry problems is even no matter how good that you are with mental math, you want to make sure that you go over your answers at least 2 times, because you could save yourself from making some silly mistakes and getting some points off on an exam. Alright, question 25 has 4 parts, and this is where the math gets fun. Okay, and the rules on how to do this math successfully start on page 13. Within the 1.6, the section 1.6 handling numbers, right after the scientific notation, it starts giving you the rules on scientific notation as it applies to addition and subtraction, and then followed by multiplication and division, and then it gets into the significant figures and guidelines for using them with addition and subtraction. Really, the math begins with example 1.3 on page 16. Okay, so yeah, we're just going to begin with part A. It says 145.75, which is right here, plus, and I like how they use these brackets, 2.3 times 10 to the minus 1. So this is a number in scientific notation. So we can do this a couple different ways. You can do this really fast in your calculator, or you can do it by hand, and we'll just do a couple by hand, and then we can start breezing through them quick. But one thing that we have to point out is that the directions are asking us to express the answers of these operations in scientific notation. Okay? So whether we take the numbers out of scientific notation, and then we get our answer is going to be out of it, but then we have to convert it back to scientific notation when we report the answer. So it all depends on how you're doing it. And to remember the significant figures. So I would say the first step for A, I'm going to zoom this in a bit, is to start with this number and get it out of scientific notation. Because our n is -1, the exponent, we're going to move the decimal to the left 1. Our resulting number or value that we're given, or that we'll have, is 0.23. Okay? And then from there, we can add it to 145.75. Or actually, I'll go ahead and draw this arrow like this. Okay, we're going to add it. And it's always important, I added these grid lines in here so that we can keep everything lined up. We're going to input the number when we do these out by hand. We always want to keep the decimal points justified. Like that. See how they're lined up? They're lined up right here. You want to, as long as you do that, you should be able to always calculate the right answer. So in the end, this will be 8, 9, 5, 1, 4, right? So this is our answer, but now we have to take this into scientific notation. So our n, capital N, a number between 1 and 10 would be 1.45 2.98. And because we are moving this decimal 2 spaces to the left, our n will be positive. And since it's moving 2, our n is positive 2. Okay? So that means this is our answer. And going by the book and the solution, the number's correct. 1.4598 times 10 to the 2 power. Okay? Next, part B. We have division here. This is a division sign. So we could do this a couple different ways. We could start with this number and convert it to scientific notation, and then we could apply the division rules of scientific notation, which would be, let's do it. So let's start with this one. We have 79,500 converted to scientific notation would be 7.9 times 10, and what would it be? I'm sorry, not 7.9, it'd be 7.95, right? Because that 5 is significant. So in order to get this decimal 1, 2, and then give us 2 more zeros, we would need to move it 1, 2, 2 spots. So if it's starting here, we have 1, 2, 3, 4. So it would be to the 4th power. That's what this number is. And then we can take this number here and just bring it down. And here's our problem. Right? This is our new fraction. So at this point, we can use the rules of division, where in scientific notation, or the division rules for exponents. So since we have a positive 4 as the numerator exponent, and then we have a 2 for the denominator's exponent, we simply just subtract. We have 4 minus 2, which would equal 2. Whatever answer that we get, our n is equal to 2. So you could actually do this out in your calculator. We can do 7.95 divided by 2.5, right? Our resulting answer, or quotient I should say, is 3.18. And because we figured out what our exponent is, we can say it's 3.18 times 10 to the 2. Now we're not finished, because we're not ready to report this answer yet, because we have to look back at the sig figs. And because we have 1, 2, 3 sig figs, and then we have 1, 2 sig figs, the rules of the sig figs say that we report our final answer when doing division in the lowest number of sig figs. So since this number here had only 2 sig figs, that means that our answer has to be converted to 2 significant figures. So we have 3 sig figs here, 1, 2, 3. We need 1, 2. And since we're going to stop at this one, this 8 means that we round the 1 to a 2. So this number becomes 3.2 times 10 to the 2 power. And that's our final answer. Can't forget that last step, the significant figures. Super important. The instructors, the professors will take points off if we're not following those rules. They're in the textbook for a reason. And again, page 14, page 15, 16, and 17 gives good examples of them. Alright, part C. 7.0 times 10 to the minus 3 power minus 8.0 times 10 to the negative 4 power. Alright, so one thing to note is we have an exponent of negative 3 and then an exponent of negative 4. So we could do this a couple different ways. You can input it right in the calculator, get your answer, which on an exam and test, that's probably what you're going to do unless he requires the work to be shown, which would be a drag because then you have to write it all out, which we're going to do right here. So an easy way to do this would be to do the subtraction seamlessly. We could bring the exponents to the same value. Since we have, on the left side we have a negative 3, and then on the right side we have a negative 4. We can't raise the negative 3, we can't reduce, we can't make the left side less than what it is, right? We can't make it negative 4. So we're going to make the right side negative 3 instead of negative 4. And how we do that is we're going to turn this number 8.0 times 10 to the minus 4 into 0.80 times 10 to the minus 3. So what we did was we just moved the decimal point to the left 1. And that in turn ended up making this from a negative 4 to a negative 3. Right? And we made the number smaller. So that's where that rule came in. So now we have 7.0 times 10 to the minus 3 minus 0.80 times 10 to the minus 3. And because the times 10 to the minus 3 is the same for each, that means that whatever our answer is that we get down here, that's also going to have times 10 to the minus 3 to it. Alright? So we can simply, after setting it up like this, we can do mental math, or we can type it into the calculator to just be sure. 7.0 minus 0.80 is equal to 6.2. Okay? So that essentially is saying now that our final answer is 6.2 times 10 to the minus 3. Okay? And from the book solution, that is correct. So you can do it a number of different ways. That's a way that the textbook actually is showing. So we can move on to the next one. D. We have multiplication here. Okay. So what would we do? We have two numbers in scientific notation already. We have to recall the rules of sig figs. We have 1, 2 numbers here, and 1 and 2 numbers here. So that means that our final answer is going to have 2 sig figs. And with the rules of multiplication and exponents, we simply add the exponents together. When we had division, we subtracted them, right? An earlier situation here, right? We had 4 and 2, we just subtracted them. But now, since we're doing multiplication, we add the exponents. Sorry. So we can set this up as however you want to do it. 1.0 times 10 to the 4 times 9.9 times 10 to the 6th. What this actually will come out to is a number times 10 to the 10 power. So 1.0 times 9.9 is equal to 9.9, right? Anything times 1 is whatever the number is. And we have our 2 sig figs. So the book solution states 9.9 times 10 to the 10 is correct. So that's right. So these problems at first looked a little bit like they may get you nervous, but when you come up with a strategy on how to tackle them, really the math behind it is pretty much mental, you know? So, but it's all about knowing how to approach these problems and being able to identify what am I doing at first, multiplying, dividing, addition, subtraction, things like that. And you have to try and decide how you want to approach it, whether you're going to keep your answer, your values, your original values in scientific notation, or if you're going to convert them to non-scientific notation. And since the question is asking us to express the answers in scientific notation, that's what we have to do. So we can move on. Alright, so 26 has 4 parts, A through D. We're going to do A right now. Express the answers to these operations in scientific notation. So just similar to the last previous problems. We have 0.0095 plus 8.5 times 10 to the minus 3 power, or negative 3 power, is equal to a number in scientific notation. So first things first, we identify what we're dealing with. Addition, right? We're doing an addition problem. We want to come up with a strategy that works for these addition and subtraction problems. So we have to think, let us express scientific notation as n times 10 to the n power. When adding numbers using scientific notation, we must write each quantity with the same exponent, n. So since we want to do that, we can then add the n, the capital N parts of the numbers, keeping the exponent n the same. And that's similar to what we just previously did. So let's start with this left side. We have 0.0095. So in order to make this number a number such that it has an exponent of negative 3, what would we do? We have to write 0.0095 in such a way that n is equal to negative 3. So we have decreased 10 to the n by 10 to the 3, or to the third power. So we must increase n by 10 to the third. Okay? So we have to move the decimal point 3 places to the right. As a result, we would have 1, 2, 3. And that would be 9.5 times 10, right, to the negative 3. Because we had our original number and we went to the right, we're assigning the value of the exponent negative 3. Now we can go ahead and just bring this number along, right? 8.5 times 10 to the third. We can just bring it over here and add it. 8.5 times 10 to the negative 3. Okay, now we're actually just ready to do the mental math. Okay, because the times 10 to the negative 3 power isn't changing here, we just simply can bring it right down. Whatever answer that we get is going to have that times 10 to the negative 3. So in the calculator you can put in, or you can do it mentally, 9.5 plus 8.5 is equal to 18. Right? 18.0. So we're not finished yet though. Sorry. Let me just fix that 0. So as you can see here, we have 18.0 times 10 to the minus 3 power. This isn't in scientific notation yet. Why? Because when it's in the standard form, remember, n times 10 to the n has to be a number between 1 and 10, and 18 exceeds 10. So we need to turn this 18.0 into a number between 1 and 10. How are we going to do it? We're going to use 1.8. So, since we moved this decimal here to the left 1, that means that we have to increase the exponent by 1. So we basically add 1. So negative 3 plus 1 gives us what? Negative 2, right? So that means our answer is 1.8 times 10 to the minus 2. Now, our standard form of scientific notation is right here. 1.8 times 10 to the minus 2 power. I'm sorry, it should be 1.80. There we go. Because the 80 is significant. So let me just bring that up. 1.80 times 10 to the negative 2 power. And that, my friends, is how we can approach some of these problems here. Alright, 26 part B. 653 divided by 5.7 times 10 to the minus 8 power. Express the quotient in scientific notation. So, let us express scientific notation as n times 10 to the n power. When dividing numbers using scientific notation, divide the n parts of the numbers in the usual way. So the capital N. I'll just call it n prime. As n capital. N capital or capital N is what I'm denoting as n prime. It's just easier to say and shorter. So to come up with the correct exponent n, we subtract the exponents, like I mentioned before. The rules of exponents and division, subtract them. In multiplication, you add them. So here, first thing first, we're going to convert 653 to scientific notation. How we do that? Well, we can look at 653 with an imaginary decimal point here after the 3, because it's a whole number, right? So it could be we could look at this number as this, 653.0. Now, since we're going to move the decimal point in original form over to the left 2 spaces, we now have 6.53. And if we're going to complete the standard form of scientific notation, we have times 10. And what's our n? Well, since we moved to the left in the original form, that means our exponent's going to be positive. And in this case, since we moved 2 spaces to the left, our n is positive 2. Okay, and I'm just putting brackets around it. So this here is now our our numerator of the division problem. So we can go ahead now and just take this number and bring it into our denominator. So now we have 5.75 times 10 to the minus 8. And I didn't change anything about this number right here. Okay, as you can see, what we're working with now is this division problem. I just converted that number here to scientific notation. Okay, so with the rules of division, we can simply subtract the exponents. We're going to deal with these portions first. Okay? So 10 to the 2 power over 10 to the minus 8 power is just like saying, since we're going to subtract them and we're just dealing with the exponents here, is plus 2 minus negative 8, which then becomes plus 2 plus 8, giving us plus 10. So whatever answer that we get now is going to be times 10 to the 10 power. Okay? So we just took care of these areas, the times 10 to the n exponent. So let us now handle this 6.53 divided by 5.75 as normally we would do it. You can do it mentally if you can, or by calculator. 6.53 divided by 5.75 is equal to quite a number, 1.13565217.4. But when we look at the sig figs, we have 1, 2, 3 in the numerator and 1, 2, 3 in the denominator. So that means that we're going to keep 3 sig figs. 1, 2, 3. Okay? Since we have a 5 right here, that means that we're going to round up the 3 to a 4. And it's going to become 1.14. Okay? And we can forget about these digits. So then we can bring the times 10 to the 10 power, and that completes our answer. Okay, that's our final answer. You can input this into the calculator and I'm sure you're going to get this answer, 1.4 times 10 to the 10. Okay? And in the textbook, the solution is correct. 1.14 times 10 to the 10 power. Okay? Hopefully these explanations help. We can move on to part C. Alright, so part C. This is a good example right here that is a good practice of the rules of the trade. The tools of the trade. So we're given a subtraction problem. Okay, first things first, we identify subtraction. we're given 850,000 minus 9.0 times 10 to the 5th power. So our first step was to identify the operation, which was subtraction. Next, the easiest way to do these is to convert the non-scientific notation numbers into scientific notation. So we'll start with the left side of the problem. We have 850,000. We can look at this number as 850,000 with a decimal point right there. Although I drew this 0, it is not significant, okay? But I'm just writing it there to hold the place on the side of this decimal. So since this is the original form that we're given right here, it resembles this. We look at the decimal where it is, and in order to get this into the standard form where we know n times 10 to the n power, where n is a number between 1 and 10, can't be less than 1. We'll see that pretty soon. This little rule here come into play. So we have to move it 1, 2, 3, 4, 5. 5 places to the left. So we know that the n will be positive 5 of the exponent. Okay? So that means that our n prime, which is the capital N, is going to be 8.5. 8.5. And we said the exponent would be positive 5, right? Because we moved to the left of the original number 5 places. So we just converted this non-scientific number to scientific. Okay. So then we can just write the subtraction sign, and what we're going to be dealing with. I don't really want to have brackets there. So we have 8.5 times 10 to the 5 power minus 9.0 times 10 to the 5. And I'm sorry, I totally forgot. It just worked out this way here, that conveniently converting 850,000 to scientific notation, 8.5 times 10 to the 5, this times 10 to the 5 just so happens to be the same as what this number is using. Because similar to the addition and subtraction, we want to keep the times 10 to the n exponent the same, because if we do that, if we have these the same, then we can just focus on this part, right? Because this is going to carry, these are going to it just carries down to times 10 to the 5. So now we can actually do in the calculator, or mentally, we already know it's going to be negative 0.5, right? So this is essentially saying negative 0.5. I'm just writing it a little bit better. That this is our answer. But we have to remember here that we're not finished. Why? One could say, oh, well, it is in scientific notation. No, it's not. Because we have negative 0.5. Okay? So, what's the big deal? It's not the negative part, it's the 0.5. We can't have the number less than 1. So, going by this rule right here, using this rule, we have to change up the negative 0.5. What are we going to do? Well, we're going to go from negative 0.5 to, we're going to move this decimal over to the right 1. So now it's going to become, and we're going to keep this negative sign, negative 5 5. Okay? And that's what we're going to do. Now we're going to make a change to this portion, the times 10 to the 5 power. Since we went from our original answer of negative 0.5 here, we took the decimal to the right one place. Since we're dealing with a number less than 0, that means that we have to decrease the exponent by 1 because we moved one place to the right. If we moved 2 places to the right, we would subtract the exponent by 2, but that's not the case here. So since we moved 1 place to the right, we subtract 1 from the positive 5 right here, and it becomes positive 4. So now our answer is correct. This is our answer here to part C. We just write it in. Negative 5 times 10 to the 4 power. That's our answer. And by the book, this is the solution. The solution set, yep. So this problem was good because it had us convert this non-scientific to a scientific notation number, and then we used subtraction here, and we converted this number in such a way where we could easily just subtract this n prime part, right? The capital N portion of these two scientific notation numbers. We ended up with a number that was less than 1, where it was negative 0.5. We note that this times 10 to the 5, it remained as it carried down here. And this is what we were left with. So because of this rule, the n prime rule, a number between 1 and 10, we had to convert again to scientific notation from here to this. And because we did that one space, we had to reduce this power by 1, and we got 4. And that's how we got this. Negative 5 times 10 to the 4 power. Alright, part D. This one's not going to be as long as the previous ones. This one is conveniently set up in a way where both left and right parts are already in scientific notation. So we note first that this is a multiplication problem. We're going to be multiplying these two numbers that are already in scientific notation. We note that it's 3.6 times 10 to the minus 4 and 3.6 times 10 to the 6 power. Okay, it just resembles this. So we could mention first, it's always important we identify how many sig figs that we have. Left side we have 1, 2 sig figs. Right side we have 1, 2 sig figs. So that means both numbers have 2 sig figs. It's multiplication. So that means that our answer will be reported with 2 significant figures. Okay? So we can look. If you look at we could do either portion first. We'll start with this, the front portion. 3.6 times 3.6. Okay. 3.6 times 3.6 is equal to 12.96. And I'm sorry, I didn't mean 3.96. My bad. Meant 3.6. Okay? So the rules of significant figures apply right here as well. They apply everywhere throughout this problem. So because we have 2 sig figs, and I'll denote it there, SF for sig figs, 2 sig figs, that means that our answer needs to have 2 sig figs. But right here, in its truest form, not rounded, we have 1, 2, 3, 4 sig figs. So since we're going to keep 2 sig figs, we stop it here and we look to the neighbor of the 2. which is a 9. So that means that we're going to, in turn, round the 2 to a 3. So this is going to become 13.00. But when it's written this way, those zeros, these zeros here, are significant. So we need to not include those. We're going to leave our answer as this, 13. So now, I'm going to change this. We can focus on the times 10 to the minus 4 and the times 10 to the 6. You see what I'm doing here? I'm taking this and just going there, and this, and going here. Okay? So the rules of multiplication, and I'm just extending this, right? Just extending this multiplication problem. Okay, we did the front portion first, and now we're just doing the times 10 to the lowercase n, the exponent. Rules of multiplication state that for exponents, we simply add them. So what this is saying is minus 4, or negative 4, plus 6 is equal to 2, positive 2, right? So that means that the answer that we're coming up with now is 13 times 10 to the 2. So this is our answer, but it's not in the correct format to record it as. So what we need to do is fix that. The usual practice is to express n prime as a number between 1 and 10, since we must decrease n by a factor of 10 to express n between 1 and 10, which we're decreasing it by a factor of 10, 13 by a factor of 10, which means that it will now be 1.3 times 10. What are we going to do to the exponent? We must increase the 10 to the n power by a factor of 10. The exponent n is increased by 1 from 2 to 3. Okay, so this here is our final answer. It meets the format of n prime times times 10 to the n exponent. The textbook solution says this is correct. 1.3 times 10 to the third power. Alright, so question 27. They're asking, what is the number of significant figures in each of these measured quantities? Okay. The guidelines for sig figs are on page 15. Those will explain the rules as to how you can identify how many sig figs. I already know them and I am familiar with them, so I'm just going to go over these. I'm not going to read the guidelines. I'm going to start with part A. 4,867 miles. How many sig figs? 1, 2, 3, 4. Look at the hash marks I'm making here. 1, 2, 3, and 4. There's 4 sig figs. And I'm just going to abbreviate it as SF for sig figs. Okay? The solution in the textbook matches this. 4. B. 56 ml or milliliters. Well, 1, 2. There's 2 sig figs. Okay, next. 60,104 tons. There's 1, 2, 3, 4, 5. 5 sig figs. Okay, and D, since there's 2,900, we only count these two. So I'm putting, at minimum, there's 2 sig figs. Okay. That's it for 27. We can move on to the next. Okay, question 28. What is the number of significant figures in each of these measured quantities? So they're measured quantities. A, we have 40.2 grams per centimeter cubed, or per cubic centimeter. So 40.2, that's 1, 2, 3. There's 3 sig figs. Okay, that's correct. As far as the book goes, the solution. And B, we have 0.0000003 centimeters. So there's 6 zeros in front of the 3. And that means that there's only 1 sig fig. Okay, and that's correct. And for C, 70, there's no decimal or anything. There's 1 sig fig. And then here, 4.6 times 10 to the 19 atoms. This is going to be 2. 1, 2 sig figs. And that's correct. Alright, so question 29 says carry out these operations as if they were calculations of experimental results and express each answer in the correct units and with the correct number of significant figures. So this is like something that you would see in the laboratory, or on like a laboratory data table where you have all the calculations. You got to make sure that you're reporting the correct number of significant figures and not too many over, things like that. So we'll use these grid lines to set it up. So the first thing first, we identify the operations here. It's going to just be addition. So we set this up by aligning everything with the decimal. I'm not going to bother with the units. I'll put these off to the side here. Meters. You can just keep tabs on the units there. So we're dealing with all the same type of units. So as we can see, these numbers are all lined up by their decimal point. So we can just start doing the math. Okay, so there we go. We just added them all together. And one thing that we need to note is the number that has the least amount of sig figs after the decimal point, which is this 0.6. That's going to be the most important number here, because we're going to base our sig figs off of that number. So what that means is we stop here at the 6 and we look at the neighbor to the right, which is a 0. That's going to lead us to keep this 6. So our final answer to this question is going to be 10.6 meters. And the book provides the correct solution as 10.6. So this is correct. Alright, part B. 3.70 grams minus 2.9133 grams. We can set this up similar to that previous addition problem. Minus 2.9133 grams. If we do out the math, we're getting this for the answer. 0.7867. So the point of significance is 2 decimal places after, 2 spaces after the decimal point. We have our decimal points right here. So we went 1, 2, and that's where we're drawing the line. So we're looking at the 8 and the neighbor 6. That means that we're going to round this answer to 0.79 grams. And the textbook confirms this solution. Okay. Alright, part C. 4.51 centimeters times 3.6666 centimeters. So it's a multiplication problem. So considering the rules with multiplication and significant figures, we count the sig figs in each side. We have 3. And then on this side we have 1, 2, 3, 4, 5. 5 sig figs. So our final answer will be rounded to 3 sig figs. Okay, because we go with the least amount of sig figs. So when we multiply these two, 4.51 times 3.6666, we get an answer of 16.5366 to be exact. And since we're going to keep 3 significant figures, we are counting from the left. 1, 2, 3. We have a 5. And we look at the neighbor, which is a 3, which is too small of a number to round up. So we're going to keep 16.5. And the units on this one are centimeters. And by the... Oh, actually, you know what? You gotta be careful. I made a mistake. Anyone catch it? Well, I'm gonna say it. The mistake I made was the units are centimeters squared, not just plain old centimeters. So, getting a little tired here, but when we're multiplying centimeters times centimeters, we get the centimeters squared. So it's very important to not neglect those units, to make sure that we're writing those down, especially with multiplication. Alright, part D, this is the last part of this question here, question 29. So we have to identify the operations here. We have an addition, a division, and a subtraction. So here's our numerator and here's our denominator. Alright, we can rewrite this as 3 times 10 to the 4 grams plus 6.827 grams divided by 0.043 centimeters cubed minus 0.021 centimeters cubed. Okay, so I just rewrote this as a fraction, and then we can just start doing the math now. Okay. So the way I'm going to do this is, since we're dealing with addition, and we have we could do 3 times 10 to the 4 power, which is 30,000 grams. And we can just add 6.821 grams to it. That'll give us 30,006.827. Okay, and we're going to keep that true number there. And remember our units, grams. And then we have 0.043 minus 0.021. Okay, which gives us this. 0.022, and the units on the bottom here are centimeters cubed. So we can go ahead and divide this now in the calculator. Alright, 3,000 or 30,006.827 divided by 0.022 is giving us the number 13,000. Oh wow. No. 1,363,946.682. And we have to keep 2 sig figs. Wait a minute. Okay. We missed an important step here, so this is a good example. This portion right here, we need to redo it. Because when we look at 3 times 10 to the 4, this is 1 sig fig. Okay? So if we were to translate it, we said it was 30,000. And then if we were to add 6.827, we can actually hypothetically place a decimal point right there, and there aren't any digits after this decimal point. So in theory, that's where we stop, right there. So when we do the addition, we are left with 30,006. Okay? We could say, oh yeah, that's gonna make it now 30,007, right? Because the 8 is gonna round up. Okay, let's see. Okay, I understand. Now, since we have this is correct, 30,007. Now we need to place the denominator that we got from this, 0.022 centimeters cubed. And now we have to do division, and we have to recall the sig figs to this. And since it's division, we report our final answer in the amount 1, 2, 3, 4, 5. 5 sig figs up here versus 2 sig figs. Yeah. Yeah, I'm not too sure where the book is getting this number from. But the textbook has the solution for this one as 1 times 10 to the 6 grams over centimeters cubed. I'm not too sure how they're getting that. I don't know what I'm missing. Yeah, I don't know. 'Cause my answer I'm getting is 1.4 times 10 to the 6. Yeah, I don't know. I guess this is just conflicting. I don't know. Maybe if someone else can give an opinion and then leave a comment. But I kind of disagree with this, for sure. I'm going to put a little note near this one. Yeah, that's a problematic one.